Okay, so Rocha is a postdoc in the laboratory for astrophysics at the Leiden Observatory, and he obtained his PhD in Brazil, and since then he has done postdocs in Scotland and Denmark. And his research is focused on the use of laboratory experiments, computational modeling, and astronomical observations to learn what molecules in solid phase can teach us about our astrochemical origins. So thank you very much, Will, and Mr. Floor is yours.
Thank you very much for the introduction. And also thank you, Professor Serena, for the nice talk. So save a lot of time for my talk as well. Okay, so let's talk about ISIS. So Professor Serena already talked about these molecules in space, also in the gas phase and solid phase. And my talk will be basically about solid phase. And I think I'll try to answer. So I'll try to answer some of the questions that people asked for the talk. Okay, so and also let's talk about James Webb, because it's something that's taking a lot of attention in the news, and I think this is also important to talk about here in Leiden as well. Okay, so this is the James Webb Space Telescope. So we have this picture when it was like in this French Guiana, and this is the size of the telescope. So we see that's very big compared to the other space telescopes. And it was launched into space on the Christmas Day last year. And we see here the moment of the launch, and also this nice picture that I like quite a lot. This one here, that was like leaving the spacecraft. Okay, so you also saw these nice images from the telescope that is targeting different conditions or environments of the space. And this is not like random pictures, but actually it's addressing different goals of this telescope. So first we have this picture here that's about the early universe. So we have a lot of galaxies, and this is a beautiful image of these galaxy lengths as well. We also have this from the exoplanet. This is a dying stars. These are also other galaxies, and this is the part that I'll talk about tonight. That's about stars that are being formed in this week. So, yes. So this is actually a very big part of the scientific goals of this telescope, and this actually dedicates a lot of time, of operational time, of James Webb to study the formation of stars and also the formation of molecules in space. Alright, so let's put a little bit bigger now, and this is a very beautiful image of the James Webb in different filters, different wavelengths, and basically what we're seeing here are these stars that are not like young stars, but then we see these small points that are stars that are being formed in this molecular cloud. And actually we say that's a molecular cloud because, as Professor already said, we have a lot of hydrogen, molecular hydrogen, that's H2, but also have dust. And these conditions in these clouds, if you go for the very deep parts of this cloud, we go for this minus 263 Celsius degree. That's very cold. And this is enough to form the complex molecule that you want to form. So as I said, then we have this small dust. This is not like an interstellar dust, this is actually interplanetary dust, but we think that should be similar also in the interstellar medium. And also have A2 and hydrogen. That's actually the major component of these clouds. But actually what we're seeing here in this image are mostly dust emissions. Okay. So now that we know something about these molecular clouds, I want to show this video that shows how, for example, ices can be formed in space. And this is a nice video because it's part of the actual program that was about the telescope that has a strong participation of the Netherlands. And specifically about the formation of water ice, they created this video that's very interesting. So please, if you click there. So if you go for these regions in this molecular cloud, we see, for example, the distance that's very big Here you have, for example, 2 light years. But then you can contrast with these small dust grains. That's 0.1 micron. And the surface of these dust grains, some atoms can collide and stick there. So we have oxygen and hydrogen. They react with each other and can form water ice, for example. And then sometimes we saw, because of the excess of the energy, they go to the gas phase again, but they can dance a little bit there. And now we have formation of O2, and then another hydrogen coming, another one, and then we have hydrogen peroxide. If one comes, then it becomes stable, and then you have the formation of water again. But then if you just accelerate in the time, what you see here is basically the formation of a mantle that we call ice. So this is the formation of the simplest ice, one of the simplest ice in space, the formation of the water ice. Okay, but perhaps this scenario is a little bit more complicated because we also have nitrogen, we also have carbon. So instead of only water ice, we may also have CO2, we also have carbon monoxide, methane, also formaldehyde, some ions like CN minus and then NH4 plus. And it becomes a little bit more complicated when we include to this context the presence of radiation, like for example cosmic rays and UV, ultraviolet, because this can process this material and form even more complex organic molecules. Okay. Sorry for that. Yes, so the point is, why to bother about these ices in space? And the answer is because we want to understand how far this chemical complexity go. And then we can just look for this picture here and see that in our body we have all these chemical elements. And this, as was, I think was one of the questions from Selena's talk about the formation of these chemical elements in space. But also it's interesting to think about this reflection made by this famous astronomer. I think you guys know the name. What's the name? Sagan, right? And then I think that's very important. We are made of star stuff. So this is a claim, right? If you do astronomy, we see that these are formed in the stars, but actually to go beyond the presence of these chemical elements, we have to form the molecules. And then we have to test this, okay? So this is intimately related with the question about the origin of the life on Earth. So basically we have 2 theories. One says that we have formation of these complex molecules on Earth itself, and also could be something coming from the space. So I think the answer for this problem is not simple, but actually is a correlation between the 2. So to test this, then we have to go into space, and then we have to use big telescopes, like for example James Webb, to answer these questions. So how to test this hypothesis, that life could also be, the ingredient for life could also be formed in space? Right. First thing, we need laboratory experiments. And there was one of the questions about if you can simulate this, mimic these conditions on Earth. And the answer, Professor Anna said very well, is yes, we can do it, but of course we have some limitations, right? So, for example, in this experimental setup here, that's in the Leiden Observatory, we can reach, for example, conditions of 10 Kelvin, and also pressure of 10 to minus 10 millibar. This is not right the same that we have in space, but it's close. And that is good enough to make some assumptions about what we have in space. So basically what we do is that in this part here, we can put like these small tubes, that's for example could be water, and then the water vapor goes inside this chamber here, that's cooled to this temperature, and form ice. So the gas come here, condense onto the substrate, and then we have the formation of the ice. So this is one of the things that you can do. And if you put this ice against infrared light, what we see is this kind of bands. And each of these bands are related to vibrational modes of the molecule. So the molecule is not static. Okay, so basically we have some vibrations of these molecules, Each one of these vibrations, like for example the carbon and oxygen, or the carbon and this hydrogen, creates one of these absorption bands. And this is how we know that each of these bands could be present or not in space, because we can compare with the astronomical observations. And I will show this a little bit more later. So, another thing that was also one of the questions is about the complexity that you have in space. And actually, we already know how to form glycine, that's the simplest amino acid, in the laboratory. So in this work here, basically, what was done is that people included in these experimental chambers some hydrogens and oxygens and carbon, and they can react together without any radiation. That's only low temperature chemistry. Okay? And then we know that it goes further and further into the formation of glycine. That's the simplest amino acid. So this is formed, could be formed in space. We know that's formed in the lab. The question is this formed in space? But now, if you include, for example, radiation, I would say ultraviolet, you can form something that's much more complex. That's the ribosyme. That's a key ingredient for the formation of the RNA. Okay, so this is also formed in the lab, could also be formed in space. Good. So we see chemical complexity in the laboratory eyes, but do we see it in space eyes? Well, if we look for this spectrum here, this is a spectrum of a high-mass protostar observed in the 90s, and basically we have different absorption bands associated with different molecules. And actually, we see that water is the most abundant ice that we have in space, but we can go a little bit like the small components, like this one here. So, if you look for this very small portion of the spectrum, we have these black lines here. And then we can compare with these laboratory experiments that I just showed for you. And here, for example, we have a good match of these molecules, that's acetaldehyde. And also here could be the presence of ethanol that I think you guys are drinking a lot tonight. Okay, so ethanol could also be formed in space and acetaldehyde as well. So, now we see that chemical complexity in space as well, but how to go deeper in this research? Well, then we need the James Webb Space Telescope. And the reason is because this area of the telescope can go just collect more and more light, and then we can go much deeper in the sensitivity and just detect very small abundances of these molecules in space. Well, we have some programs that are being led by some professors in Leiden. So for example, we have the ERS Ice Age, and basically this program was one of the first scientific programs to have observations dedicated to ice with the James Webb Space Telescope. So that was like an important thing. And also we have the JOICE, that's called James Webb Observations of Young Protostars, that's led by Professor Ivina van Soek. So we have a lot of data, which is keeping me a lot of busy as well. And yeah, and I'm allowed to show just small parts of the observations that we have so far, but there's much more to come. So let's talk about this one, JOICE. So that's the Professor Ivina van Soek, and this is the spectrum of one of the protostars that we have. So basically here we have the absorption band related to the water ice, and also here we have this other one that could be methanol and Na+, methane. This is the silicate, that's the dusty grain, and this is the CO2 band. One of the nice things that was completely unexpected, so when I plotted the spectrum, I was not expecting to see that big. That's this red spectrum here overplotted on the black. So the black is the same that we're seeing here, but just without this band here, that's the silicate. So basically, this molecule that is formic acid. This molecule was not observed before until now. Okay, so we had like different observations with different telescopes, space and ground-based telescope. We never saw this molecule, although it could be there, but we never saw it precisely before. That's the first time that we see this molecule in a protostar. So we have also other program. Unfortunately, this is the only thing I can show. There is much more to come, and then I say to you that stay tuned because this is important. Like we have a lot of observations coming from this program, and basically we have already a paper that was submitted to a journal. They expect like the final decision about these two protostars. Sorry, these two objects. It's not a protostar. The reason is because it's a cloud. But in this cloud, we don't have any star formation. It's only the cloud. So we don't have the presence of radiation or anything like that coming from the star. So it's something that's very pristine. Okay? And we are reaching like very deep in these two objects, and the chemistry is very peculiar. So, yeah, stay tuned about this because the results will come soon. I would expect that at least 3 weeks we have the paper published. So let's. Then it would be a nice opportunity for another astronomy update as well. But yeah, but this is the only thing I can show about this problem. I cannot say more, but this is a very interesting problem. So my take-home message for you is ice boosts the chemical complexity in space. This is important. Ices are important to make building blocks of life. And also, James Webb will help us to tell more about our chemical origins in the next few months and also the next years. Thank you very much for that.
Question for Will. Okay, maybe let's start last time.
Yeah, I've got a question about aromatic chemistry.
Yes.
Red giants have a lot of aromatic species around them. Do they play a part in your consideration?
Yes. So this is actually a big problem to us because when we see this absorption spectrum from space, we have lots of these aromatic emission that basically call like PAS, that's polycyclic aromatic hydrocarbons. And then we have to remove them to understand the ices. So that's part of our consideration. Yes.
So, if I understand correctly, correct me if I'm wrong, then the previous speaker focused on emitting lights, molecules that emit lights, and you focus on actually absorbing light, right?
Yes. Although I can say that this is for the range where James Webb observed, but if you go for the far infrared, some of these ices have thermal emission, so you can also see the ices emission. That's also very interesting. Unfortunately, we had a problem that we had a telescope to be prepared that was called the speaker, and then like during the construction of this telescope, it takes a lot of time, like from the scientific ideas to the project itself. And this was one of the problems by ESA, but unfortunately, this was like discommissioned because the lack of money. And then we won't have any 5-4 telescope for the next 40 years. That's very unfortunate, but perhaps we have the next one that's called, I think, Louvois in the 2050 perhaps. Yes. But then we could see ices emission there.
Any more questions for Will? It is turning on the discussion. Well,
Here, Miguel. I hear a lot about I hear a lot about dust and about the molecules that form around it. But what is dust? Is that not also molecules?
Yes, these are also molecules, and basically it's composed basically by silicate. So we have silic, and then we have oxygen. We also have some inclusions of magnesium, iron, and this could be the silicate. But also, that's the band I showed here in this part of the spectrum. That's the strong that we have, and also here. That's S, I, and O. But also we have some inclusions of carbon. The point is that we don't detect carbon because it's basically flat, so we don't have any absorption band. But if you want to do some modeling, like in a computer, of this spectrum, we need to include carbon, otherwise we don't fit anything. So it seems that carbon is there.
Well, if there are no more